Good morning, friends, or good afternoon, or good evening, whatever it is where you are. Happy start to the 5th week of class. This is going to be our final week of thermodynamics, and we are going to make a go at some optics starting this time next week. Well, starting this time next week. We got the first celebration, so starting Wednesday, I guess, of next week. So we've got, in terms of things going this week, we've got PLC 5. Oh, I have to post that. So that's essentially a celebration review. I call it a traffic light. There's a few other things going to be involved. It's going to be a slightly different format. You're going to have to submit a picture of your work in this one. I can't turn this one into a quiz format so easily. So I'll get that posted up. That's going to be a situation where you basically grade yourself in terms of topics that we've talked about. How do you think it's going? Do I feel like I can get this one pretty well? Do I feel like I can get this one pretty well? How is it feeling for you? Are you needing any help on some of the topics? And then if you do feel like, yeah, I could use some more practice, how are you going to do that? Are you going to find some more problems? Are you going to look back at some homework problems, rework the celebration problems, that kind of thing? So we're going to get you started on that, and there's a couple of extra ones on showing that violations of the second law occur when you consider different cycles. Last time I think I showed you just the zero heat flow cycle with work being produced. Well, and then I showed how that violated the Clausius second law. Same ideas kind of going on with that one, but one flow heat cycle instead of zero flow heat cycle. So we'll take a look at that. So that will be for Friday this week as usual. And then homework 3, I think I posted that already. That'll be due Tuesday. And that will be when celebration 1 is. And for you folks, labs 4 and 5. So lab 4 and 5, right? So that's last week and this week, is the design your thermodynamic project, and that means proposal is due today. And given approval on that one, you can get started. So proposal is due. And that's 3, 4. Is today the 4th? Today's the 4th. So proposals due today. Submit those in on Canvas. I will take a look at them and get back to you later this week. So if you have time, you can get started. And then the Lab 5, which is going to commence on Friday this week, will be kind of go ahead and start doing your data taking, doing your thing. So it'll be a continuation. All right. After that, your presentations for that are due the following Friday. This Friday will be the 7th, and then your presentation for that will be due on the 14th, which is the following Friday after you had it. So you get a full week of work in on it. All right. So any issues on that, let me know. Fire me an email, and we'll get started on some topics today. Having talked about entropy last time, we talked about entropy. We looked at the entropy of an ideal gas and some of the different processes that happen. We looked looked at the definition of entropy. We looked at some situations. PV graph, we looked at a few processes in which entropy increased, and we did an example of entropy decreasing, and just examining the mentality of the law or the idea of the entropy increase is that if you're finding the entropy decreasing, it's kind of like a mentality of an energy conservation. I'm not looking at it big enough of a system, right? It's not that we don't believe in the energy conservation. It's that, oh, I find that energy is not conserved in this part. What about the surroundings? What other things are interacting with it that I'm missing, right? So then it kind of turns into an issue where you're chasing down, hold on, where can I find these other things? And the same thing's true with the entropy. You're going to find the entropy decreasing, as we did in that water droplet example. And then you can say, well, where must it be increasing? And you're going to think about what's taking the heat away, right? I've got some system that's actively trying to cool this droplet down and remove heat from the system such that I now need to reject that heat somewhere. Not to mention the process by which I am taking the heat away from the droplet is typically an entropy increasing process itself. And now I have this heat and I got to get rid of it. And it goes out into the atmosphere where it increases the entropy more than the entropy decreased here with the droplet. So, a fun kind of thing to think about. What I'd like to do here is go back to starting on heat engines and talk a little bit more about efficiency in refrigerators and engines, and link in the entropy, how the entropy became an interesting quantity via looking at the heat engine. So, what we'll do is we'll start looking at heat engines here. And I've made a few adjustments to the video quality. I have tried to research. I've heard from a few of you, so appreciate the feedback. I've tried to research ways to getting better video quality here, and I think I'm at least going to give it a try, and hopefully this will be okay this week. Or not this week, but this time. Take a look at it. Keep after it.
Yeah, it's, as always, it's a simple, small checkbox, and it took more than a couple hours to find the little checkbox. So, what are you going to do? All right, so let's talk about heat engines, and let's start again with the same usual heat engine schematic that we have for the simplest possible allowed heat engine by the Carnot second law. Where we've got a heat drop into the cycle here, we've got work being produced, and there's a heat dump like an exhaust into a cold reservoir.
Now remember, the circle indicates the cycle. This is a, for example, piston cylinder device, or you could think of it as a PV diagram that's closed, or whatever it is. The idea is that this is a cycle such that the internal energy of this has not changed. So you could consider, for example, the energy flow according to the first law. Which would tell us that the internal energy being Q plus W, the internal energy change of the cycle should be zero, so our Q and W should be equivalent. This is zero for a cycle. And therefore Q is zero, Q plus W is zero. Now, remember that when you have quantities like heat and work flowing in and out, we have to make sure we get the signs
reasonably well figured out here. So let me try and schematically draw what the energy flow, maybe, looks like here. It's going to be something where if I consider the QH here, the heat flowing in from the hot reservoir, maybe I can do this as a thing like this. So we're gonna consider a large amount of heat flow coming in here. And I'm going to essentially siphon off some of that in order to take some work from that heat flow. All right, so I'm going to take some of it and it's going to come out like this. Let's see, I can go a little further with that one. Is that about right? I've taken one off here and two are dumping. All right. So what I've got here is an idea that, like, as if I had a big pipe here and there was fluid flowing down or through it somehow, right? I'm going to siphon off some of it to go this way and do usable work for me. And the rest of it, I'm going to have it come down here, and this is going to be the stuff that I'm going to be throwing away. All right, so what I'm going to do is I'm going to say that this is basically QH here. This is QC here. And this is the work here. So now all that's left to do is make nice pretty arrows. So what this is telling you is, if I look at the first law, right, energy is conserved. So there's work going out there. There's heat getting dumped here, and the outgoing should equal the incoming. Well, it's not quite listed that way in the first law. That's not how we wrote it. But ultimately, this here is telling us that Q equals minus W. But what do we mean by Q? I've got two heat flows here. I'm going to have to think about the signing, the algebraic signs of these quantities. Remember, they are referenced to as if you are sitting in here and looking around. And you're saying, okay, I got QH coming in, so that's an adding to me, and then QC is leaving, that's a negative. So Q is really like a sum of the two. Excuse me. This is really a sum of the Q's based on what their algebraic signs are. All right, now what that means is I'm going to have QH as being positive and QC being negative, and that's going to be what's going in here. Work leaving, right, essentially is saying that that work is going out. Q equals minus W. Did I get that right? Yeah. So that's essentially saying that the work is leaving. So that if I thought of the total heat that the system absorbed, the total heat absorbed would be a lot, but then we reject some of it. The leftovers hopefully is doing usable work for us, and that usable work is leaving us and is negative, and therefore this QH minus QC should turn out to be a negative W, but W itself is negative, right? And this is going to turn into just the work that's going. So if you reorient it to the idea of incoming equals outgoing, like maybe a normal energy process you have, then you'd flop the QC onto that side, and you'd see that the incoming QH should equal QC plus W, which is the leaving on both of these sides. Remember, in the time this was happening, Carnot did not have access to the ideas of energy conservation in this way. They were more working on the idea that heat itself was conserved, which was a difficult thing because it was producing so many problems. And they weren't recognizing work as being
same type of thing, like an energy transfer, as heat is, until Rumford came along and started saying, well, wait a minute, I think work and heat are the same thing. There's a mechanical equivalent here. And then Joule came along, and then so they started realizing that. But Carnot didn't have access to the idea of the first law. So to him, it was all something to be deduced. To us, it seems very straightforward, but to him, it's something that he was still working on. Okay, so in this case, if we want to talk about, for example, the efficiency of the engine, then the efficiency, our basic definition of efficiency here, which we use as the epsilon. The efficiency is essentially what we want to produce, what is it we're trying to get, divided by how much do we have to put in order to get that. All right. So basic definition of the efficiency is what we get out divided by what we put in. So in this case, what we're getting out, well, we're getting out two things. We're getting out the QC and we're getting out the work. Certainly the work is the one that we're hoping the engine is giving us. In other words, we'd really like to maximize that. Unfortunately, it turns out for most real engines, which run on irreversible cycles, the process is more like this, where I'm taking off. If you notice, I've tried to make this reasonable. I'm not sure if you can actually see the grid lines on my board here, but I've got a 3-space QH here, and I'm siphoning off one of them here, and the other two are coming here. So I am trying to visually also obey energy conservation, so that's a nice thing. In this case, we're going to have work divided by QH, which was our necessary input to attain the desired output. And therefore, the bigger and bigger we can make the bigger and bigger we can make the W, then the larger amount of energy that we had input from the QH is getting transferred into something that we want, and that means that this ratio is going closer and closer to 1. But I want to point something out. I want you to notice something here. In that work, in this thing here, we're going to have the idea that energy is conserved. So we got a little bit of glare right on top of that. So if I go stand here, no, it doesn't help. Oh, if I go stand right there, aha, there we go. So the work via energy conservation is the difference in the two heats that were transferred, okay? And now if I take that idea and I plug it down into here, I'm going to see that I can make this efficiency expression a little bit more interesting. Since the work is QH minus QC, then efficiency becomes QH minus QC divided by QH, which we can write into slightly more interesting form by dividing this through. And we end up at this idea that the efficiency is 1 minus, in other words, the efficiency is 100% less how much exhaust did you have compared to how much input you had, all right? The idea of minimizing this QC is the idea of reducing this such that this can become bigger, right? The exact same thing as what we were just talking about with the work. So if I take a greater fraction of the QH and turn it into work, I have a lower amount of QC left over as basically exhaust. Now, notice, according to the Carnot second law, the simplest possible heat engine has how many heat transfers, right? It has no fewer. It must exchange heat with no fewer
than 2 reservoirs, which means that I always have to have an input heat coming from a hot and an exhaust heat dumped into a cooler reservoir. Otherwise, this is not a valid heat engine. Notice that the first law makes no qualms about, it has no qualms about this, makes no efforts to deny this, because according to the first law, as long as I have an input amount of energy which is accounted for in the output, everything's fine, right? And so this is the thing that I've kind of been talking about a little bit as we've been going on, is that the idea of the first law does not deny that I should be able to take all of this heat input and turn it all into work, so that I throw away 0 of this. Were that to happen, you can see that my QC would be 0, and then I would have an efficiency of 100%. And this is called fun. It's also called unattainable according to the Carnot second law. The Carnot second law, which as we now know is equivalent to the Clausius second law, forbids a single heat transfer engine. No fewer than 2 heat reservoirs, right? You can have as many as you want as long as it's more than 2. Therefore, QC can never be 0, and our efficiencies always will be less than 100%. And that's even with the idea of a reversible engine, okay? Remember, the idea of reversibility is essentially that we are trying to do things in the best possible way, in the most ideal possible way, okay? Therefore, we're able to get an upper limit. If we consider the best possible way to do this, such that there are no losses in taking the system through a cycle, then we are essentially saying that there's no possibility we can do better than that. And even with no possibility of doing better than that, we're not going to reach 100% here, because QC can never be 0. And that means the efficiency is always going to be less than 1, or it's always going to be less than 100%. And that's the ideal case, right? The ideal case you're operating at, the best possible thing you could do is get to 80%. And we typically will fall well short of that, okay? Okay, so in this case then, I want to take a quick diversion and just ask, since we know that it's not possible, right? What this is telling us, it is not possible to have work out equal to QH. Not possible that the work equals QH, and therefore that the efficiency would be 100%. Cannot happen. Even in the most ideal engines. So now I want to ask if I want to kind of take a turn to that. I want to adjust that a little bit. And what I want to ask is, suppose that we thought about, instead of QH coming in and work in QC, we know we can't turn all of this heat into work. Is it possible that we can turn all of the work into heat? Is that a possibility? Would it be possible, rather than saying, I can't make a 100% efficient heat engine by taking all the input heat and turning all the input heat into work? That's not possible. Is it possible I make a 100% efficient transfer from work into heat? Can I do 100% efficient transfer of work into heat? Is that a possibility? Is it possible that that happened? Well, the answer is yes. Maybe you had a little bit of time to think about it, but the answer is yes. It is possible to take a 100% efficient process of input work turned into heat. Yes, we can do that. That doesn't violate any second law problem. Because the input work, if you can look at it as a couple of different ways, right? The input work can be turned into heat because the Carnot statement is saying that the restriction is on cycles that exchange heat with no fewer than 2 heat reservoirs and produce work, right? In the second law statements, it's always about producing work. There's nothing that says this can't happen, where I input work here and it all gets dumped into, say, QC or something like that. We do this all the time at 100% efficiency. A resistance heater, for example, is a situation where I'm taking electrical input work, I'm heating up some coils, almost like a toaster, right? Toaster coil, like a red hot glowing coils. I'm taking electrical input work and converting it into heat. And whatever I'm putting in there is leaving as heat. So heat's going to be generated essentially with every real and irreversible interaction that we're going to deal with. It's like one of those bank transfer fees, right? If I want to move money from here to here, they go, oh, yep, no problem, here you go. Oh, that's gonna cost you just 0.5%. And you go, oh, okay, that's great. Actually, I changed my mind. I need to get it back over to here. Oh, no problem. Well, that's going to cost you 0.5%. Doesn't matter which way you go. They're always going to take a little bit out, right? Same thing with heat. Heat's always going to say, I'm just going to take a little bit out. Because for real irreversible processes, which is what happens for us here in the real world, there's always going to be friction. There's always going to be turbulence. There's always going to be some type of viscosity, right? Something's going to happen that's going to become a loss, which is why we consider reversible processes as an idealization to that. And then we know what we could possibly shoot for and understand that we will never get there. All right, so a resistance heater can definitely work it can definitely take input work and transfer it all into heat. This is allowed, and that's a yes. Okay, so let's take a look at a couple of cycles here. So we're going to take. Actually, I wanted to do something before I did that. No, I guess not. We're going to take a look at a couple of cycles here. So, for example, in terms of gasoline engines, let's look at the efficiency of gasoline engines. These are real engines. So we haven't restricted this yet. This is still a real engine efficient, as long as it's a 2-flow heat cycle and not a multi-flow heat cycle, like 5, 6, 7 stages or something like that. As long as we've got a 2-flow heat cycle, then this is the efficiency of it, how we calculate it in any engine, whether the engine be ideal or whether it be a real irreversible one. We still would calculate the efficiency this way. So a gasoline engine, for example, might, during a cycle, one full 4-stroke thing. Now these are more complicated than what we're dealing with here. So we're going to idealize it a little bit. The gasoline engine operates on what's called the Otto cycle, and it looks something approximately like this. It's called the Otto cycle. Otto, not automobile, Otto, for somebody named Otto. If I were to sketch this out on a PV graph, it would look something like this. Oh dear, it's off. We'd have we would model the piston moving as essentially an adiabatic process because it happens so quickly, right? And when the heat is injected, typically what happens in a four-stroke engine is intake air is pulled in, the piston compresses really quickly. It doesn't compress like a diesel engine, but it compresses. And then the spark plug fires and the whole thing explodes. And at that point, the piston gets pushed this way. So we're going to consider an adiabatic compression, a heat input at constant volume, a power stroke, which is an adiabatic expansion. And then at that point, a little bit of, and then some magic happens. We'll assume the heat leaves during approximately the stage when it's constant. I understand there has to be another stroke in order to get that exhaust gas out and then pull new stuff in. So it's not quite exactly what's happening, but it's a nifty little idealization. So we'd have a heat input here at constant volume. We'd have two adiabats going like this and like this. So we'd have something along the lines of that, where these, Q is equal to 0, and they are adiabatic. All right. Again, this is an idealization of that, right? It's not. Yeah. Anyways. So you can think of it as this. Suppose that we injected 10,000 joules. Here's QH happening right there. QH happens there. QC happens down here, which it has to because that's these are the only options, right? QH has to happen here and this thing's kind of going in a clockwise type of manner. Adiabatic compression that way. Isovolumetric heating. Adiabatic expansion, isovolumetric cooling. So since these are adiabatic, the only possible choices for an input heat is here and an exhaust heat is there. So this is fairly straightforward. Suppose that we have an input heat of say 10,000 joules. Make it nice and easy. Oops. All right, suppose we're going to deal with a 10,000 joule input heat and a work per cycle of, say, 2,000 joules. The work, remember, is still going to be found the same way as we've been doing, and that would be this area here. That area is the work done. During the cycle. So suppose that we did that and it's 2,000 joules. Therefore, we'd know that the efficiency is essentially work over QH. I understand that there's a lot of I'm going to take a step back here for a minute. I understand that there's a lot of equations to manipulate, but really remember, it was the same way in 4A or 4B. So think about what we're doing, what are our laws, and when we started this class, we were going to look at the ideal gas as the backdrop. All right. So what all these things are doing are they're coming from applications of the ideal gas as a model to the thermodynamics as a system viewer. Right. So So it's not necessary to. Maybe it's necessary, but I don't think it is. It's not necessary to try and memorize work over QH or 1 minus QC over QH or any of these other things. I got to memorize all this stuff. No, you just have to remember this works within the first law, right? If I remember the basic definition of efficiency, what do I want out? Divide it by what I put in, then I'm all set. The efficiency here then would be work divided by QH. And I think you can see that would be basically 0.2. Yes, it must be unitless. We're dividing two energetic terms, so those are going away. This is a typical efficiency for a gasoline engine car. Your QC in this case is the leftover, and that's 8,000. So it's 20% efficient, but it's 80% not efficient. How about that? Now, there are many other cycles that we can look at, but one of them I do want to look at is the Carnot cycle. And this is going to be a bit of a lens as to how entropy got established. All right, so let's take a look at the Carnot cycle. So Carnot, in addition to coming up with lots of the ideas about second law stuff and thermodynamics, also tried to think of an engine cycle that he could work with. And so, of course, now it's called the Carnot cycle or the Carnot engine. Oops, Carnot engine. And this is a set of 4 processes which forms a cycle. Okay. Draw this one nice and large so we can see it. Where we're going to talk about an isothermal compression followed by an adiabatic compression, followed by an isothermal expansion, followed by an adiabatic expansion. What he's doing is he's taking 2 of the adiabatics and connecting them with isotherms, or if you like the other way around, isotherms connected by adiabatics. But essentially, let's see if I can get this drawn out approximately correctly here. So if I think about an isotherm, okay, so maybe there'd be an isotherm going like this. Let's start here and have it go to, say, about here. All right, so that'll be my first stage. This will be isothermal compression. Let's call this 1 and 2, or let's call this A and B. Let's do that. Let's call this A, and let's call that B. All right, so now I'm going to draw the next isotherm up. And when I do an adiabatic compression, I'm going to jump from this isotherm to that one because adiabatic crosses isotherms. And then we're going to slide down that isotherm, and then we're going to connect up the rest of that to the start of this one here. So let's go like this. Here's my next isotherm here. I'm going to connect this up with an adiabat, which is going to go up like this. Oh, that's terrible. No. Oh, it's very bad. Maybe I want to scoot that in just a touch. I'm not super happy with that one. Like that. About like that. So this would be point C here. This is Q equal to 0. It's going to slide down. We're going to slide down here on the isotherm. say to about there. Here's point D, and then it's going to be adiabatic going like that. Okay. Something maybe near to that. The idea being that it's two isotherms connected by two adiabats. All right, and that's the Carnot cycle. So let's take a look at what we can figure out from this thing. Let's start by considering a piston cylinder and looking at the cycles as run as if it was a piston cylinder with a gas inside it. So an isothermal compression. Here's our piston cylinder. At point A, at state A here, it's going to be isothermally compressed to get to point B, which means its internal energy is not changing. The temperature is not changing, the internal energy is not changing. So you could imagine here at point A, I put a bath around it or something like that. So I put a way for it to maintain its temperature. All right, so this is a reservoir. But it's at constant temperature, as all reservoirs are. And I've got a piston in here. And I've got a little tray up here such that I could slide a mass on and off it. All right, now for example, if I took the mass and I kept the reservoir here, and I'm going to do an isothermal compression and then an adiabatic compression. So what's going to start, so it's always hard to kind of start the thinking of these things. But effectively, I'm going to start with pushing a mass on top of this thing and having the piston go down, which is going to cause the gas to compress, but I'm allowing it to leak out. I'm allowing heat to leak out into the reservoir. All right, so then by the time I get to point B, the piston's going to be slightly down, right? And I'm going to go like this. Heat left, and I don't want to draw it on one particular, I can't draw that at one state, but let's suppose I have for example, a QC leaving, or something like that. I'm going to take away my reservoir. I now have the piston is compressed slightly, so it's down here now. Maybe I've got a mass sitting on top of this thing. So it's compressed. Now I'm going to, instead of having the reservoir there, I'm going to take the reservoir away and put insulation around it. Now I'm going to fix the insulation such that heat can't get in or out. So now this is insulation. And I can drop, say, for example, another mass on top of that. Now I'm not letting heat in or out, so it's doing work. It's going to compress it down a little bit further. And we're going to rise up to a higher temperature. At which point we're going to remove one of the masses, right? We're going to keep the piston. I'm going to remove one of the masses. I'm going to remove the insulation first, put it in a nice bath, and a nice reservoir at this temperature. I'm going to remove the mass. It's going to slide down here. It's going to expand it isothermally, right? And then I'm going to do the same thing. Take that bath away, put the insulation on, remove that mass, and it's going to expand adiabatically. Right? So it's essentially the same type of steps here with that. So I'm going to have a situation here where I'm going to compress the piston even further.
I'm going to now put it into a hotter bath. Oops, this isn't all the way up there though. This is only a bath. So it's only here. If you're interested, that's one of the differences between my reservoirs and my insulation. The reservoirs only go up to where the gas is, and the insulation goes around everything. All right, so no heat out, but work was done on the system by putting the mass on it, so it's going to, right? And now I'm going to put this in here. We're at a hotter temperature. We're at TH now. This is TC down here at point A, and point B. We're still at TC at point B, right? Yep. Okay. Work was just done. No heat was transferred. Okay, now I'm going to put it in here. I'm going to remove one of the masses. It's going to flip up, right? So by point D, I'm going to have this thing coming up. I'm going to take heat in. I'm going to remove. It's going to raise the masses a little bit, right? It's going to remove that mass and. I can slide one of those masses off as it moves it upwards from the heat input. There. And then I'm going to swap it for insulation. And this is point D, and this is still at TH. And we move it in. So I did QC coming out. Let's see, QH is coming in as we do C to D, so QH is going in here. Right? So same idea as with the Otto cycle. When I look at the PV diagram, there's really only two possibilities for where heat could be transferred. Right? I'm going to get a QH and a QC from the two isotherms, right? Because I have no possibility of transferring heat in the adiabatics. So I've got a QC getting dumped here between A and B. I got a QH entering here between C and B, and that's causing the work to happen. And then we're removing the masses and having an adiabatic expansion, and then we're back to point A as we take the insulation off and re-put the cold reservoir around it. So when we do that, we can also calculate work that's get done, because work is getting done at every single stage here, right? We can calculate the work done here. Let's calculate some works. We already know work done. So work done during an isothermal process would be, for example, this C to D process. That's the work done by the system. Work done on the system would be from A to B here, as well as B to C in an adiabatic part, and work done by the system D back to A adiabatically. Right? So work done isothermally, then we know that delta E internal is equal to 0, and therefore work done is minus integration PdV. And we explored this a little bit already with in the first week when we talked about isothermal processes. And we were able to write P in terms of V, because when the temperature is constant, then the right side of the ideal gas equation of state, nRT, is constant.
So we're able to write it as nRT divided by V dV, where nRT is a constant, and we end up getting the log of the volumes, right? So then we end up here with negative nRT, and we're going to do the log of V1 to V2. Here, V1 and V2, so we'll do the natural log of V2 over V1. And so if V2 is greater than V1, as it would be going from C to D, then the log is a positive number, and that's a negative sign here indicating work is leaving the system. And that's the thing that the engine wants. No, that's the thing we want out of the engine, is for work to come out of it. Pursuant to that, you will often see in some textbooks they do write the first law with a Q minus W convention. And that is because they call work leaving an engine a positive thing. Okay, whereas we're looking at, that's more of an engineering distinction, whereas we're looking at the science of distinction, which is everything is system-based. So if work leaves the system, we call it negative. If you're an engineer and work leaves the system, you go, yay, I got work, that's positive. So sometimes you'll see the first law written as Q minus W. We write Q plus W and then have this convention for the work. Isothermal work happens like that. And then if you wanted to think about adiabatics, then what you could do, and this would be true for whatever V1, V2 you wanted to talk about. If you wanted to talk about adiabatic work done, so this would be the isothermal. The adiabatic work done, remember what we do with adiabatic is we look at PV to the gamma, or say P1 V1 to the gamma is P2 V2 to the gamma, as being a constant. Okay, so we're going to go back to the definition of work, and we're going to say, all right, well, I needed an expression for P, and that's going to show up with V to the gammas in it, and we're going to have to integrate those. Now, that's one way to do it, and it will work because this is the definition of the work, and this is true for an adiabatic process. However, one of the other, maybe more simple ways to do this would be to look at the first law and recognize that the internal energy is equal to the work. So if I'm sorry, the change in internal energy is equal to the work. For an adiabatic, since I have no heat transfer, if I can get my hands on this delta E internal, which for an ideal gas, as long as we know what the temperatures are, right? If I have temperature T1 and T2 and they're known, then I should be able to turn around and figure out what's this change in internal energy, and that would be the work done. All right. We have a fun little offshoot that we can get to here based on P and V for an adiabatic. Let me just see if I can work that in over here. Since for the pressure, we can use the ideal gas equation of state to write the pressure in terms of the volume, right? I could say that this pressure 2 here is equal to nRT2 divided by V2. Okay, that should be allowed by the ideal gas equation of state. And I could also do the same thing here for P1 and say there's nRT1 divided by V1. What then is going to happen is I'm going to change my variables from P and V into T and V. Okay? If I do that, then what I'm going to find is that I'm going to get nRT1 over here times V1 to the gamma, but I'm also dividing by it, so it's gamma minus 1, and that's going to also equal nRT2 times V2 to the gamma minus 1. Okay, since X and R is a constant for our processes. We can neglect those, or just, we don't have to neglect them, we can actively cancel them out. And that means instead of PV to the gamma, I also get the opportunity of writing T V to the gamma minus 1 is equal to constant for an adiabatic. So that all falls under the heading of adiabatic. And this does the same thing as PV to the gamma. Okay. All right. Okay, so why is the Carnot cycle useful? I guess what I want to say here is, remembering that when I have an adiabatic process, no heat's being transferred, and therefore we call that a constant entropy process. Okay, Carnot didn't call it that because he didn't know about entropy, but the idea being that the entropy increase is all happening along the isotherms, okay, along the A to B and the C to D. That's where the entropy is happening for the Carnot cycle. All right. Now, I'm going to go back to the idea of the efficiency. 1 minus QH over Q, oops, no. QL over Q, nope, QL, where's that coming from? QC over QH. Okay, you never can tell these days. And we've talked about the idea of QC not being able to be 0. So, what happens here is that with the idea of the entropy being constant, because this is a reversible process, right? If we're going through and we're saying, okay, I'm gonna have no entropy generated here or here, but I want to think about these isotherms, okay? Because clearly here I'm gonna have a heat input. That's where my QH is happening, and my QC is happening here. So with the heat transfer comes entropy, right? And what I want to ask is, if I can just redraw the schematic here, TH and TL, TC. Now I got L stuck in my head. Okay, I've got a QC like that. Now with the heat transfers, I should be able to say, with a reversible engine, okay, I should be incurring zero entropy with the engine itself, okay? The engine itself, delta S should be equal to 0 because it's reversible. This is getting too complicated here. I'm going to erase that. Let's start that over. The cycle itself is reversible. And it is re-attaining its original state variables. Remember, entropy is a state variable. So if I start here and I slowly and reversibly work my way around an adiabatic, and it's going down, and I come back here, my entropy should be exactly what it was when it started if I do it reversibly. All right? For a reversible cycle, no entropy generated. Okay, so it's operating at the very bare minimum of satisfying essentially the Carnot idea, Carnot-Clausius idea. Okay, really it's the Clausius idea, but that's okay. So this is operating at the very best possible level that it can. Not generating any entropy, there's no sliding extra friction, there's no turbulence, no viscosity, nothing is going to be lost. It's reversible, and it's reattaining its original state variable. Therefore, if I think about what entropy is getting generated, then it must be getting generated by the heat flows. Is generated QH. Okay. Now, if I take a look at the situation from the reservoir standpoint, entropy is generated by QH. So the delta S for the hot reservoir my delta S for the hot reservoir, it is able to maintain a constant temperature while heat gets transferred out of it. So this had an entropy decrease, right? Its QH was negative, but its TH is constant. So this delta S would be equal to negative QH over TH. Same idea for the cold reservoir. That delta S of the cold reservoir now from the cold reservoir's perspective, QC is getting dumped into it, so it would be a positive QC over TC. All right, so there's an entropy decrease and an entropy increase. The cycle itself should be not contributing any extra entropy. It's running at the bare minimum of satisfying the delta S, the Clausius inequality, the delta S being 0. Therefore, if we think of the best possible scenario, the best possible scenario is the entire thing doesn't generate any entropy. And its total change is equal to 0. If that's the case, then I should be able to write that the total entropy change is 0. In order to make the best possible scenario out of this, total entropy change be 0, that means that delta S equals 0, and therefore this is delta S total, and that means delta S H plus delta S C should equal 0 because the delta S of my cycle is already equal to 0. Therefore, since this is an entropy decrease, this is an entropy increase, therefore they must equal each other. In other words, negative QH over TH plus QC over TC should equal 0. And therefore, QH over TH should equal QC over TC. Okay, this is remembering that we are trying to create the best possible scenario under which we could get an upper limit on our efficiencies. Okay, the best possible engine is going to increase the entropy of the universe by absolutely nothing. We know it can't decrease it spontaneously, right? It shouldn't be able to do that. But it's satisfying the bare minimum of this inequality that these entropies of the reservoirs should be equal in this way. Now notice what we can do at this point. If I say swap the QH down here right? And I form the fraction QC divided by QH. QC divided by QH, if I pull that down here, I'm going to have to swap it with the TC. That's going to equal the ratio of the temperatures. And partly it was because of this that Lord Kelvin came up with the idea that, look, we can have an absolute temperature scale. The absolute temperature scale is really predicated off the Carnot engine. And it's based off this efficiency right here. Not efficiency, but it's based off this heat ratio. What Kelvin said is, I can take these two heats and call that temperature ratio the same thing, and these two temperatures are going to be the establishment of the absolute temperature scale. So it's not necessarily an ideal gas issue, it's actually the thermodynamic temperature, and therefore the absolute temperature, is actually due to the Carnot heat engine. And it's due to this expression right here. That means what I can do is I can take my efficiency and say that, well, I just erased it. Well, I'll just rewrite it, QH. Now I can take it and make it into a Carnot efficiency. So for an engine, I can measure what the hot and cold operating temperatures are and say, okay, the best possible thing I can do in this situation is take this real engine, throw it away, replace it with a Carnot engine that is reversible, that operates between the same two temperatures. What efficiency would I get for that Carnot engine operating between these two temperatures? And that's going to be the best possible efficiency that I could get for any engine operating between these two temperatures. Therefore, our real engines, which are irreversible, will fall short of this number, because this is our idealized case. All right, this is called the Carnot efficiency, and it represents the efficiency of a Carnot engine which is operating between the same two temperatures as the real engine that's outputting the heats. All right? So it's as if we took that, threw it away, and swapped in a Carnot engine. And now we're going to ask, what's that efficiency going to look like? That efficiency, I'm going to call this efficiency with a Carnot subscript here. Because I have the ratio of these heats, I can just replace them with the ratio of the temperatures and say that it's this. That's the Carnot efficiency. Now you can also see where the third law comes from, or our fourth thermodynamic law type of thing, which comes about by saying, equivalently, when Carnot was saying you can't eliminate this, it's that you can't reach this temperature. The TC is not reachable. TC being 0 is not reachable. That's the case in which you'd have a 100% efficient Carnot engine. But even a Carnot engine, which is the idealized best possible scenario, cannot reach 100% efficiency because it's got this TC over TH fraction out here, and you can't make TC equal to 0. All right, and that's via kind of the Nernst proposal, the Nernst postulate. TC cannot be 0. All right, so a little bit of hand waving on how that works, but essentially it's something like this. All right. Okay. So if we spend today on engines, we can spend tomorrow on refrigerators, and we'll do an example. I'm gonna ask one question here, and I think we're gonna be just about wrapping up. So let me ask this. So if this is our Carnot efficiency, which it is, what's a better way to increase this efficiency? what's a better way to increase the efficiency based on the temperature ratio? Should we increase the hot temperature reservoir, or should we decrease the cold temperature reservoir? Which one do you think is going to be which one's going to be a bigger increase in the efficiency? Which one's kind of the better thing to do? More bang for your dollar, right? That kind of thing. What's going to be the better thing to do? So imagine that we just tried this out and put a little math behind it. So we ask, is it better to increase TH or decrease TC? Okay, ultimately we're trying to make a better engine here, something that's more efficient. So let's look at the Carnot efficiency as 1 minus TC over TH, and let's allow the temperatures, let's take the temperatures to become a temperature plus a delta, or something like this. All right, so I'm increasing the temperature a little bit, or I'm going to decrease the temperature a little bit, plus or minus, and see what happens to the efficiency. So let's start by increasing TC. Let's start by increasing TH. If I increase TH, the Carnot efficiency becomes 1 minus TC over TH plus a little bit. Right? Now, if I'm going to say, well, this is a small number, maybe I could make it a little smaller even if I took a ratio. Suppose that I took a ratio of 1 minus TC divided by TH times 1 plus, delta over TH. Like that. I could factor that TH out of the bottom. I could rewrite this as 1 minus TC over TH, which is what you're used to, times this extra factor. It's in the denominator. So it would go to the minus 1 power right there. And if this is truly a small number, such that delta over TH is much less than 1, right, in comparison with 1 here, then I can use the binomial approximation on it, and I can say that the efficiency is approximately 1 minus TC over TH, and I'm going to multiply that by 1 minus delta over TH. Okay, so that makes this go down a little bit, right? It's this is a number which is less than 1. It's 1 minus a smallish number, so this is a small number. That makes this go down a little bit, which increases your overall efficiency. Let's compare that to what happens if we just decreased TC a little bit. So if I decrease TC, I'm going to get my Carnot efficiency becoming 1 minus TC minus delta over TH. And so that's going to look like, if I just factor this out, or whatever it's called, TC over TH, and I've got this thing in here, that's going to be 1 minus that, TC minus, so this is going to be plus delta over TH. So now I can say that that's something similar to, wait a minute, is that right? Can I do it that way? I think I can, because that minus should go through here and it should go into there. So this is taking what used to be the efficiency here and increasing it by a small amount. This is, let's just find out what this is doing. 1 minus TC over TH here, and then that factors through here, and it's adding TC over TH times delta over TH. Right? So I would say that this should be the winner because this number is less than 1. So you're adding a number that's that's lower here than this number here. This number is less than that number. So actually decreasing TC is the better thing to do. Try to make your colder a little bit colder, and you'll find that your efficiency goes up a little bit more than if you tried to make your hot hotter. And on that note, I will say that we have reached our end of cycle today, and we will pick up talking about refrigerators and a little bit more with an example on a cycle that we'll look at next time, and we'll try to put a few numbers in and look and see what happens. So I'll say happy day to you and look forward to tomorrow when we can explore a little bit more of Carnot cycles and Carnot efficiencies, and then also looking at Carnot refrigerators. So until then, I say happy day to you folks. See you next time.